Please welcome OFC General Co-Chairs Nick Fontaine, Fotini Karinu, and Elaine Wong.
Good morning. On behalf of the IEEE Communications Society, the IEEE Photonics Society, and Optica, we welcome you to the 50th anniversary of OFC.
Over 15,000 people from more than 80 nations have come together in person to experience the world's premier optical networking and communications event.
This week, we will learn about the breakthroughs that are ushering in the next generation of communications technology. But while this conference is all about creating the future, this session begins by looking to the past.
So it's 1970, and scientists are on the verge of a significant breakthrough. It was known that ultra-clear glass fibers could carry signals across many kilometers, but it would require the fiber with losses of 20 decibels per kilometer. That year, scientists machined a rod from titanium-doped silica showing that fused silica could be drawn into a single-mode fiber. And later that summer, 210 meters of this fiber were tested and recorded a loss measurement of 16.9 dBs per kilometer. The successful demonstration of low-loss fibers and the first room temperature semiconductor lasers laid the groundwork for developing practical fiber optic communications.
Just 5 years later, the precursor to OFC, the Optical Fiber Transmission Conference, was held for the very first time. For the next 50 years, thousands of OFC participants have been responsible for significant technical achievements to increase the bandwidth and the reach of optical fiber links. These are essential advances that have powered the internet, video streaming, high-capacity wireless communications, and many other data services.
That is why it's not uncommon to find OFC power users who have attended this conference for years. So this part will require some audience participation. So if you've been attending OFC for at least the last 10 years, please stand up. Let's give them all a round of applause.
Now, if you have been attending OFC for the past 20 years, please remain standing. All others, please take your seats.
This is so wonderful. Now, next part. If you have been attending OFC for the past 40 years, so we're talking about 1985, 40 years, oh, wonderful. Please remain standing. Oh, my goodness. We have some goats in the house, greatest of all time. Now, I wonder, now this is curiosity, right? I wonder, for those who are still standing, did anyone attend the first OFC in 1975? We have 1, 2, oh my goodness. Vincent Chan. That's right, and David Payne. Thank you so much, and thank you so much for your support. Thank you so much, everyone, for your support over the last 50 years. It is so honored to have everyone in our midst.
All right, let's celebrate again, everyone, with a big round of applause. Thank you.
So whether this is your first OFC or your 50th OFC, all of us know that this conference is all about making connections from node to node, from data center to metro networks, and from person to person. It is indicative of how fast our industry is evolving when topics that are presented at this year's OFC were barely on the horizon a decade ago. So we're talking about integrated sensing and communications, the synergy of optical, mobile, and satellite, and quantum communications.
The diversity of the technical content presented at OFC is exemplified by this plenary session. The talks that you will be about to see reflect some of the most impactful and exciting work being done today. The dichotomy between faster network port speeds and efficient massive-scale data centers, the development of high-quality 351 silicon, and the opportunity for new communication capabilities through space-based optical comms.
After these talks, when the session concludes, the OFC exhibition will be open. We encourage you to experience it and engage with our exhibitors. This year, 685 companies are participating. In total, a huge 170,000 net square feet of exhibition space. This is the largest OFC exhibition since 2003. In addition, the show floor is where you'll find industry-focused programs, interoperative system demonstrations, and OFCnet. We encourage you to attend sessions from MarketWatch, the Data Center Summit, the Network Operator Summit, and industry programs addressing topics from components to standards. Those programs are quite essential to understand market trends and the state of the industry.
A conference of this scope only happens through generosity. From our corporate and media sponsors who generously offered financial support through to our volunteers who were equally generous with their time. 250 individuals have worked tirelessly since the last OFC to construct the technical conference and show floor programs that you are experiencing this week. These committee members reviewed nearly 1,200 paper submissions, the second highest number of submissions ever in the history of OFC. They sessioned almost 800 technical talks and curated the content of panels and special sessions. So Nick, Fotini, and I sincerely appreciate the efforts of this year's program committee and the leadership of its chair, Mei Du, Lara Garrett, and Xiaodan Pang. Thank you so much. Let's give them a round of applause.
Thank you. And now, we start the session with our first presenter, Dr. Pradeep Sindhu. In many ways, Pradeep's career parallels the trajectory of OFC. From redefining how the hardware and software of internet routers are built, to advanced technologies for computing and AI infrastructure. His early work led to Sun Microsystems' first high-performance multiprocessors in 1992. 3 years later, he saw the need for high-end internet routers that was not being met by the industry. This realization led to him found Juniper Networks in 1996, where he served as its founding CEO, and then most of his tenure as vice chairman and CTO. Over 19 years, he worked on most of the company's products, including the architecture of its first, the M40 data router. This router played a major role in the development of the internet. In fact, all routers and switches today are built on the architectural principles invented in the M40. Today, Pradeep is my esteemed colleague at Microsoft, where he's a technical fellow and corporate vice president of Silicon. He is currently leading efforts to develop data processing units to improve the performance, reliability, security, and agility of Azure data centers. He has also contributed to the design of networks for AI. Please welcome to the stage Pradeep Sindhu.
Good morning, everyone. It's really a pleasure and an honor to speak at the 50th anniversary of OFC. You know, the last time I was here was a decade ago, exactly. And my, how things have changed in that 10 years. But some things have not changed. 10 years ago, I was talking about the future of transport networks. And in that talk, what I said was that electronics and optics are largely complementary. Why? Electronics is very, very good for doing computing and storage. And optics is very good at transmission. And those fundamentals have not changed. Well, today, what I'm going to talk about is scaling data centers. More precisely, I'll be talking about why, if you keep increasing network lane speeds, that actually hinders your ability to scale data centers. So that's the topic of the talk. Next slide, please. So let's first define terms. What is a network lane? So a network lane is a physical interface over which there is a single, indivisible packet stream that flows, such that this packet stream can go to one and only one connected device. So that's the definition. Now, of course, this packet stream starts out as a symbol stream generated by electronics and ends up as a symbol stream generated by electronics. So with that definition, let's also say what a network lane is not. So if you package up a bunch of packet streams and put them into a module, that's not a lane. That's many lanes. Okay? So for example, for DR8, the lane speed is 100 gigabits per second, not 800, as an example. So what is the data center scaling problem? This is another definition, so that we have the definition of lane, we have a definition of what does it mean to scale data centers. Well, what it means to scale data centers is connecting a very large number of compute nodes to each other, somehow. But it's not just connecting them any which way. It's to connect them, the most valuable way is to connect them such that any node can talk to any node. Now, that's the ideal. And of course, you want to connect them at high bandwidth, low latency, ideally zero latency, but laws of physics don't permit that, low cost, and of course, very high reliability. Now, unfortunately, laws of physics and economics force upon us a set of constraints that require us to organize these data center networks into at least three, what I call bandwidth latency domains. The highest bandwidth, lowest latency domain is called scale up. The next one is called scale out, and generally the scale out network spans a very large building in the data center. And then, of course, there is the inter-data center problem, where it could be either metro distances or even very long distances, like 1,000 kilometers. Now, at OFC, I do need to take the trouble to say this clearly. This is not the same thing as sending a large amount of bandwidth point to point from one place to another place, which is very far away. This is where optical fibers actually started. But the problem inside the data center is different. The problem is to connect many things to many things. Hopefully that is clear. Now, there has been a historical push to just keep on increasing lane speeds. Some of us will remember back in 1980, there was a building where I used to work at Xerox PARC. Ethernet was at 3 megabits per second, if you can believe it. That was a long, long time ago. And then it went to 10 megabits per second, 100, a gigabit, and so on and so forth. And today, what we're pushing is lane speeds of 400 gigabits per second, even though the PHY layer is still at 200 gigabits per second. So the case I want to make to you is that if we keep increasing these lane speeds, you are going to compromise scaling data centers. And I want to make that argument clearly. So this is the core of the argument. Scaling lane speeds far beyond 200 gig is going to hurt us. Why is it going to hurt us? There are two reasons. Number one has to do with network topology. This is a mathematical argument. It has nothing to do with physics. So if you look at that little picture, the circle with a whole bunch of spikes, that is intended to represent a network switch or an endpoint. And these little spikes are the lanes that are coming out. Now, it should be clear that the total bandwidth coming out of this object is equal to the number of lanes multiplied by the bandwidth per lane. Of course, at any given point in technology, the total bandwidth of a switch or a NIC or even a GPU is fixed. It's not arbitrarily large. And it's fixed by technology. So if I increase lane speed, I'm going to decrease in proportion the number of lanes. This should be clear. And when you decrease the number of lanes, you actually compromise your ability to build networks. This is the problem. Okay? And this comes from the fact that you're trying to connect many things to many things. So if you wanted to go point to point over long distances, you can increase the lane speed all you want. But even there are limits. For example, the limits imposed by what is the bandwidth per lambda. You can have many lambdas, but you can't make the bandwidth per lambda be arbitrarily large. So what's the problem with decreasing radix, which is the number of lanes? Well, this is, again, pure topology. When you decrease the radix of switches, the number of layers that you need in the network to achieve the same scale actually increases. And more layers causes a lot of problems. Congestion is harder to deal with, network congestion. Remember, we're talking about packet switches here, not circuit switches. So it is possible to get congestion. When errors happen, which invariably they do, it's hard to recover from them. That's another problem. So also, increasing the number of layers increases the cost and the latency. And it decreases reliability. So there's nothing really good about increasing the number of layers in a network inside a data center. But there's another problem. And this one has to do with technology. And this problem of technology has two layers. Let's talk about both of them. The bottom layer is the phi layer. And remember, these signals start out in electronics and they end in electronics. So somewhere there's a poor little transistor wiggling its wires. And trying to get transistors to do this much, much faster than 200 billion times a second is hard. You start to need exotic transistors, and that is not good. It's not good for using the standard technology for silicon, which is CMOS. You start needing BiCMOS and silicon germanium and so on and so forth, and indium phosphide. This is not helping us. Okay? It's much, much easier to keep the lane speed, the physical lane speed at 200, and then increase the number of lanes. Now, there is another problem on top of this at the next layer. And this is the packet layer. So this is, again, done by electronics. So for example, when you go from 200 gigabits per second to 400 gigabit per second lanes, even though you stay at 200 gig in the physical layer, the packet rate is now twice. Well, at 400 billion bits per second, the packet rate is exceedingly high. It could be as much as one packet every clock, or multiple packets every clock cycle. This doesn't help us design things any easier. Things get pretty hard. So the lesson that physics and mathematics is trying to tell us is, let's stick with the sweet spot that technology enables for lane speed. And that sweet spot, both at the physical layer and the logical layer, which is packet forwarding, and the topological, the mathematical, is 200 gig. Okay? Obviously, you don't want to carry this argument too far by making the lane speed smaller and smaller, because that causes its own problems. So there is a sweet spot here. And what I will keep arguing throughout this talk is that that sweet spot is 200 gigabits per second at all the layers. So one thing that you might ask is, why are people going to higher and higher lane speeds? Well, first reason is that it was actually fairly straightforward to do in the early years. And it was important that this happened. Second reason is that this data center problem did not hit us until, let's say, 15 years ago. The need for extreme bandwidth inside data centers. And I would argue that the need for extreme bandwidth did not start until the arrival of AI as a problem to be solved. And this was with the release of ChatGPT in 2022. Another reason is HPC, so high performance compute networks. Well, in HPC, there are a large number of fine-grained reads. What is fine-grained reads? This is reads of 64-byte quantities, because essentially you're trying to address memory from any computer to any other computer. And if you're doing a lot of reads, small reads, you need low latency. There's no getting around that. Fortunately for us, neither general purpose compute nor AI, especially AI training, require this ultra low latency. Okay? So this extreme push that was caused by HPC and led to InfiniBand and other fabric technologies is not necessary for AI or general purpose compute, especially. So a quick sanity check. Let's do some math. Let's assume that we're operating at 200 gigabits per second and 1 kilobyte packets. Okay? Since you do want low latency, you don't want to send very long packets. So let's take the example of 1 kilobyte packets. Well, the serialization delay component of latency is only 40 nanoseconds. Doubling from 200 to 400 is going to buy you 20 nanoseconds. This is only 4% of the typical one-way, or the minimum one-way latency you can expect when you have a few hundred compute nodes. So you can see that this is, it's not buying us anything. So this push to ultra-low latency is actually going to hurt us. There's one other reason that the push for low latency hurts us, and this is a lesson that I think certain companies are going to learn over time. Congestion becomes harder. Okay? And then recovering from errors becomes harder. So why does congestion become harder? Well, if you have two entities that are communicating over a network, in order for A to sense that B is congestion, or there is some congestion on the way, you need a round trip. No marketing talk is going to address that fundamental issue, that you need round trip. Okay? So if you squeeze the latency to the point where I cannot do that communication properly, well, you have problems. And so this is why the congestion problem is still largely unsolved in networks that do this hop-by-hop congestion control, as an example. So since we are talking about scaling data centers, data center networks, what is a good solution for scaling these networks? Number one is pick a sweet spot for lane speed, and that is currently 200 gigabits per second. Now, this speed is fast enough to mitigate the impact of serialization delay, but it also is slow enough that the implementation is straightforward. And I think sometimes we try to complicate things too much by trying to climb Mount Everest when there is no need to climb Mount Everest. Then what you must do is use chip and board level design to maximize the radix, especially the chip level. So this is the point that whatever shoreline bandwidth you have available for the network on a chip, on a package, you should use that for making more lanes at 200 gig. Okay? So as an example, for GPUs, in the next generation of GPUs, you will likely have 12.8 terabits per second. At 200 gig, that's 64 lanes. If it's 14.4 terabits per second, which is also possible, it will be 72 lanes at 200 gig, and so on. Well, state-of-the-art switches that are on the drawing board and will soon come out are 100 terabits per second. At 200 gigabits per second, the radix is 512. It turns out, and I'll show you some network diagrams in a little bit, With these numbers, 2 tiers arranged in a class topology with controlled over subscription are completely sufficient to support 250,000 compute nodes, whether they're general purpose or whether they're GPUs for AI. Okay? At this scale, as this many compute nodes, especially GPUs, you are limited by the power you can supply to a building, not by network. And if you wait another couple of years, the switches will go from 100 terabits to probably 200 terabits. And then and GPUs will also increase in bandwidth. If you keep the lane speed at 200 gig, you're going to quadruple the number of GPUs it can support, okay? Because it goes up as the square of the radix, the number of elements you can support. So we're talking about 1 million GPUs. Well, you can't supply that much power into a building today, because that's roughly 3 gigawatts for 1 million GPUs. OK, so what this says is that the network techniques that I just talked about are completely sufficient to solve the problem of scaling data centers. And we're now in the regime of how do I provide enough power. But we can't stop there. Let's go up one layer to the logical layer of the network. We have to, especially in general purpose compute networks, replace this outmoded technique for sending packets, which is called layer 3 ECMP. ECMP stands for equal cost multipath. And the basic idea is that, hey, I divide packets up into different classes. And based on what class the packet belongs to, I pick one path or another path. This is a terrible way to do networking. And the reason it's terrible is that the efficiency of the network that results from this is actually quite low. It may surprise you to learn that typical general purpose networks operate at about 30% utilization. If you use this ECMP technique for AI, similar problem with AI networks. And the reason for that is that the flows are not all equal bandwidth, and trying to jam them into lanes which are equal bandwidth just doesn't work well. Okay? People might be familiar with this elephant flow problem from networking. So what is the alternative to ECMP? The alternative to ECMP, which was invented at Juniper Networks many, many years ago, it's called packet spraying. In other words, you don't anymore divide packets into categories. You just, every packet, you spread it out evenly over all the lanes that are there, so that the bandwidth that goes on each lane is exactly equal over a period of time. Okay? So that's the technique. Now, what this does is it maximizes the bandwidth. And as many of you know, maximizing bandwidth, the available bandwidth, also minimizes latency automatically. You don't have to do anything special. It also, minimizing latency, also simplifies congestion control and error handling. And lastly, sometimes the forwarding technology available in switches has been made way too complicated. And people get happy with features. Well, in modern networks, the features required are very, very simple. It's to do source forwarding on the way up and destination-based, which is classical forwarding, on the way down. So source forwarding just means that the source tells you which way to go up the network to the top level switch. And then coming down, you just look at the destination address and you find your way to the destination. This is not the way that things work today, but this is the way that things will work in the next generation. So what do we need to do as an industry? Well, we need to focus on improving key metrics. Well, first of all, for scale-up today, it's all copper. And the problem is that copper is not cutting it. Because the scale required in terms of connecting GPUs or CPUs at the fastest layer, highest bandwidth, is hundreds. And what we can sustain is several dozen. And this problem is unlikely to be solved using copper, or at least it'll be very expensive if we do it with copper. This is the one place where a breakthrough is needed in optics. And fortunately, I think these breakthroughs are around the corner with micro-LEDs and other technologies. But for optics to win in scale-up, we have to make the cost, the power, and the reliability competitive with copper. Copper is actually phenomenal as long as the distances are not large. And of course, you all know why that is the case. It's because the bandwidth distance product of optics is way, way, way bigger, many, many orders of magnitude than copper. Now, it turns out for scale-up, 10-meter reach is enough, and that is a cakewalk for optical technologies. Now, for scale-out and inter-data center, optics is already used pervasively. But what we need to do here is improve the cost, the power, the reliability, and maintain the high radix that I talked about earlier. Now, one thing it is quite important to say is that the volumes of the modules or whatever optoelectronics we provide is roughly 1 to 2 orders of magnitude across each of these layers. So let's say I have 1 unit of bandwidth inter-data center. I probably have 10 to 20 units of scale-out bandwidth inside the data center, and then another order of magnitude for scale-up. So that's the bandwidth ratio. And latency, of course, depends on speed of light and the number of hops. So if we can solve the problem of scale-up with optics, the volume is going to go through the roof, like you've never seen before. Let me now share with you the topology for a general-purpose data center network. This is general-purpose compute, where you have compute and storage nodes. And what you can see here, the square boxes are switches, and the round circles are compute nodes. Compute with, let's say, a CPU with its memory and a network interface card, or a storage node with some computation and some media and a network interface card. So those are the 2 types of nodes. What you can see here is the topology is identical at both layers. And this topology is called a class topology. It's essentially a fancy word for any-to-any. People who've studied switching history know that this topology was invented in the context of telephone networks, telephone switches, long, long time ago. It's worth noting that the same topology works at both layers, both the first layer and the second layer, the black lines and the red lines. And as I mentioned, it should be obvious to see from this picture that if you want to go from, let's say, the leftmost node in the leftmost pod to the rightmost node in the rightmost pod, there are multiple paths that you can take. And when there are multiple paths in the network, the way that packets are sent is you try to use all the paths equally. Okay? And if packets are the same size, then it's fairly straightforward. If packets are not the same size, it's also not hard. And so this arrangement for general purpose compute will give you close to 250,000 nodes. And generally, you don't need more than that in a given data center. Now, the transport for general purpose compute networks is more complicated than the transport for AI networks. And the reason is, even though the bandwidth needs are quite modest, and the complexity comes from the diversity of applications required. You have multiple protocols, first of all, at the very least, RDMA and TCP. You have varying packet sizes, all the way from 64 bytes to 4K bytes and perhaps even 9K bytes. You have a variety of flow sizes, the data transfer sizes. Importantly, you need to maintain packet order. So if node A is sending to node B, the arrival order of packets has to be the same as the transmission order. You can't have them out of order, because otherwise applications will fail. There's a very strong requirement for reliability, of course. And the bandwidth per node is about 400 gig to 800 gig and up, going up. So one thing which is really, really important to say is that we need to focus on implementation first and committees second. Now, Dave Clark in 1992 said, we reject kings, presidents, and voting. We believe in rough consensus and running code. 20 years later, with apologies to Dave Clark, I said, we reject committees and paper designs. We believe in rough consensus and working silicon, because all these transport things have now moved to silicon. They're no longer software written on general purpose computers. So an effort to develop the right transport for general purpose was actually done at a startup that I did called Fungible. And this, we did not do any committees, but there are a whole bunch of US patents that protect this technology. But we're happy to open it up if this is necessary. Microsoft today owns these patents. I should say that there are other companies which are now also pursuing the same approaches. Let me now show you the topology for an AI data center. And on the surface, it looks exactly the same as the previous one. Just the oversubscription levels are different. There is no oversubscription here. Previously, there was a small amount of oversubscription. But the numbers work out to be roughly the same. Here, the GPU bandwidth is 12.8, so radix of 64. And the switches I'm using are all 100 terabit per second switches. Again, the same technique, but the forwarding, the transport is very, very simple. Now, the transport for AI compute, you can do many, many simplifications. And because the bandwidth required is way larger than for general purpose compute, you must use these simplifications. For example, there's only one model that is required, which is copying memory from one memory to another memory. The packets are predominantly all the same size. Okay? The data transfer sizes are very large, so you can use aggressive pipelining. Importantly, there's no requirement for delivering packets in order. This is a huge simplification. Of course, the reliability requirements are still there, and the bandwidth requirements, as I said, are extreme. So in conclusion, let's try to deliver optical technology competitive with copper in the scale-up domain, which will enable us to connect hundreds of GPUs to each other or hundreds of general-purpose compute to each other. We should stop racing to higher and higher lane speeds because it's going to compromise scale. The 200 gig is a sweet spot. Flat two-tier topologies are largely enough, at least for the needs that we can see. And the same topology works for general purpose and AI. And the same solution also works for inter-data center. Packet spraying is essential for AI. It's also very, very important for general purpose networks. Okay? For the AI problem, as I mentioned, it would be good to use all the simplifications that we can, because you're not getting any help with regards to performance. And I think that's all I had. Thank you very much.
Thank you for that excellent talk. So we continue the plenary with our next speaker, Professor K. Mei Lau. On the door to her office at the Hong Kong University of Science and Technology, she has placed a sign that reads, "All roads are winding." This is her reminder to students that challenges are a constant in research. For K. Mei, these challenges are not obstacles, they are opportunities to pivot and advance in new directions. The key is knowing when and where to turn. Her own winding road has led to significant contributions to photonics research and positioned her as a leading voice in transforming optical technologies. K-May's focuses on the integration of 3.5 semiconductors on silicon using MOCVD and other technologies with an emphasis on photonic devices. Her team is currently exploring lateral aspect ratio trapping to obtain defect-free 3.5 layers on buried oxide. This could significantly benefit in integrating lasers, detectors, and other components for silicon photonics. She is an elected member of the U.S. National Academy of Engineering, a fellow of the IEEE, Optica, and the Hong Kong Academy of Engineering. She holds patents on 3.5 transistors and LED microdisplays and has founded companies with her former students based on their research. Ladies and gentlemen, please welcome K-May Lau.
First of all, I'd like to thank the organizer for having me here. I'm truly honored to give this talk to you about DII, diversity, inclusion, and integration of 3.5 devices and technologies in photonics. And mainly, I'm going to talk about two major technologies. One is this, how we integrate 3.5 devices directly on silicon by epitaxy, and the other one is the micro LED micro displays, and we're going to do it by bonding, and I'm going to tell you more about these in this talk here. And first of all, since this is a diverse audience, so I'm going to spend a minute or two introduce you what are the 3.5 semiconductor photonic devices that we've been using. And you can see here is from the column 3 and column 5 of the periodic table. And mainly it's aluminum, gallium, and indium. And for column 5, it's nitrogen, phosphorus, and arsenic. And occasionally we'll mix in some antimony. And on the left-hand side, and you'll see that this 3.5 that we have been using since the 1970s for lasers and all the active devices, this, for the optical fiber communication. And these are, you may say, it's easier devices to make. They're all cubic. And then since the 1990s, we came up with 3-nitride material. They're also 3.5. And this is a different wavelength. And this from the ultraviolet to visible. And the earlier ones are the visible to the infrared or far infrared. So now we have all the optical band covered with the 3.5. So this is showing you that how people have been doing band structure engineering. And this, it might seem a little bit like complicated, but this will show you all the choices that you have. And with the mix and match I was talking about, and you can have the energy band gap choices, and all the way from less than like point some electron volt, all the way to almost 3 electron volt. And all this combination of 3.5 materials, so you can combine them and make heterostructures, and you can use it to make very fast transistors, or all kinds of different photonic devices, depending on the band gap that you decide to use. And also one important things I want to point out from this graph here is most of these 3.5 devices, and doing this band gap engineering, you can see it's from the lower part of this graph, they're direct band gap material. That means, and these semiconductor devices, they can interact with the photons very easily because they're direct band gap. so they can exchange energy and without having to the other requirements. So now the next, then you ask why we are moving into having to integrate this 3.5 with silicon. And this probably you have seen that a lot of people have been asking, and what's more, after the Moore's law that have been going on for since the 1960s. And it's all by scaling, and it's down to sub-nanometer scale. And we are going into the angstrom era, and you can see there's a FinFET, and actually that was from a few years back, and 5 nanometer FinFET, and then the people keep on scaling. But then what's more after that? You can't scale to nothing. And so people have been talking about, let's do optical interconnects. So let's the photons do the talking. So on the top part of the slide here, and you can see all the electrical interconnects, and also even though they've been doing 3D and building skyscrapers, but then there's still a lot of the copper wires and doing the interconnect. And then also that you will see the disadvantage is the speed is lower, and also the energy consumption is on the high side. And if we move to the photonics interconnect, and you can see many of the big corporations like IBM, Intel, and have been working on this for the past 30 years or so. And that here comes the silicon photonics. And you can have a much higher speed, and you can have a lower latency, and also less power consumption. And the most biggest advantage is the bandwidth. And so this is the silicon photonics, and people have been working on is how do we use this really well established silicon technology, manufacturing technology, to do photonic integrated circuits, and so that to make it cost effective. So this has been the goal that people have been trying to get to for the past many years. But then when you do silicon photonics and photonic integrated circuits, and of course you need the light source. But silicon is an indirect bandgap material. It's not a very efficient light emitter, and also it's not efficient in interacting with the photons. So for the past 20-some years, and people have been trying to do this heterogeneous integration. It's trying to bond 3.5 devices that has been developed like since the 1970s, I talked about earlier, and onto silicon. And so, of course, the advantage of this, and you have these 3.5 devices that were grown and fabricated on the native substrates. So they are really high performance because they have been perfect for the past like 30, 40 years. And also, people have come up with the different techniques of have efficient coupling with the other components on the silicon photonics. And of course, there are disadvantages and such that you will require quite good alignment, and in order to do this, and also the yield and has been kind of on the low side. So of course this is improving, but then people have been using this technique and either wafer bonding, wafer-to-wafer bonding, or they fabricated devices and then bond the dies onto the silicon photonics. So, and this has been in manufacturing for a number of years, and by corporations and also many startups. and many of the foundries around the world have been perfecting this technology. So, but then there is another options that I'm going to tell you here. It's electronic and photonic integration, and I coined it EPI by EPI, so it's easier for you to remember. And it's epi by epi. And this, I told you earlier, it's a 3,5 compound that have been used from the 1970s. But then people have been growing these devices on the lattice match substrates, like gallium arsenide and indium phosphide. And then these lattice match substrates, of course, it's easier and being perfect. But then how about having it on silicon but direct growth? And this will make it really much easier in the foundry for integration. But then you can see on the right-hand side, and there are a lot of challenges in doing this kind of integration. And there are all kinds of defects. I'm not going into detail, but then people have been trying to solve these problems for the past 30, 40 years. And we have been doing the same. And then you can see what people have been trying to do is you starting with the material design, the device design, and grow the materials. You got to fabricate the devices, and then test the devices, and then go back and go through this cycle many, many times. And then here are the tools that we have at the Hong Kong University of Science and Technology. And we only use an MOCVD, and I call it mostly operating CVD. And these machines, you can do multi-wafers and industry, and they have manufacturing machines that you can manufacture all the LEDs, the mixed solid state lighting that you are seeing now. But here we have the traditional 3.5 and also nitride system that we grew our own devices. And since the year 2000s, and we have been trying to do this what we call the blanket epitaxy, and to make the indium phosphide and gallium arsenide on silicon. And we kind of adopt this technique, and the nitride people have been using for lattice mismatch growth. It's a low temperature and high temperature, and then there are a lot of like trying error, and you might say, and some people have been doing that. Hey, let's do it by AI, and yes, but then the machines are not yet up to that point yet. So anyway, but we have been doing this for many years, and we have demonstrated, and there's a metamorphic high electron mobility transistors that they were grown on silicon, and more than 10 years ago. These transistors demonstrate over 200 gigahertz and FT and Fmax, and we have been pretty happy with that. But then a transistor is actually, I would say, it's an easier material to grow because it's a lateral device and it's a majority carrier device, and compared with lasers. But then later on, and we decided to take on the challenge, and then we developed this template technology, and having this V-groove silicon, and then that's using the idea of aspect ratio trapping. And this aspect ratio trapping, the idea is that you create this V-groove, and you grow on this one-on-one surface, and then you trap all the defect at the bottom and the top, and you will have, well, I won't call it defect-free, but it's quite perfected 3.5 materials for you to put devices on. And this is called the ART, aspect ratio trapping, and we have developed this technology, and then we collaborate with other groups around the world, and we demonstrated quantum dot lasers, and on using this 1.3 quantum dot lasers, micro-ring lasers, and having this on the 001 silicon. And this is 001 silicons that you may see on the previous slide. It's without miscut. So this is industrial standard 001 silicon. And this, you can have quantum dot lasers at 1.3 micron. And at the same time, we also demonstrated in the 1.5 quantum dot laser, 1.5 micron band quantum dot lasers, and this is done by the MOCVD. And this, you might see, hey, what's wrong with that? Okay, that's pretty good lasers and CW lasing. But then you can see that the buffer layer that we had to grow is over 3 microns in order to have a high enough quality laser materials and for it to have a CW lasing. And then a lot of people have been asking, hey, how do we, if we do this on the silicon, and how do we do the integration? So that's the next problem, the challenge that we were looking into, and we call this a bufferless solution. And this is go back to the previous aspect ratio trapping I was talking about. If you pattern the silicon and with a high enough aspect ratio, and then you can like trap all the defect at the bottom. And this, you see here a few of the examples, like IMAT, they have been doing this quite successfully, and doing this selective growth aspect ratio trapping. And then they have demonstrated, they call nano-rich lasers. But then, there's because to satisfy this aspect ratio, and you only get the nanometer scale materials. There are not a lot of material you can use. So we, a few years ago, we began to develop this lateral aspect ratio trapping, and we just kind of turned this idea sideways, 90 degrees, and then having this lateral growth of a 3.5, and right on top of the burial oxide. And then this, you can pattern in one dimension, and then control the growth in the other dimension. And then you can have a micron scale material to use and 3.5 material to use. And that's what we have been trying to do, focusing on in the past few years. And so we have demonstrated this vertical aspect ratio trapping, that's laser arrays in the 1.5 micron band. And we have shown that depending on the Fabry-Perot cavity length, and you can cover from the O band to the C band. And so this is quite a flexible technology. And then there's a lateral aspect ratio trapping. And it's, like I said earlier, you do photolithography in one dimension, and then the other dimension, you control your growth time, and then you can have enough material, much larger material to use. And that's what we did. And this is showing you the indium phosphide membrane that we have achieved by this lateral aspect ratio trapping. And this indium phosphide, and we use, we typically try to optical pump them and to make sure if it can lace. And this is a good enough materials that we can do more. It's a kind of quick evaluation. So we have shown that this indium phosphide sub-wavelength lasers, and that is half a micron in one side, in the patented side, and the other side, and they're lasing, and by optical pumping in around the 900 nanometer range. And then we also make photodetectors, and these are high-performance photodetectors. And this is the growth a little bit more complicated. You got to have N-type, and then in the middle, and you have the light-absorbing material, and then the P-type, and then you got to have enough material that you put ohmic contact on, so that you can connect them electrically. And we have demonstrated that these directly grown material, the photo detectors, has quite high performance, and they are high speed, and also the detectivity was quite good. And then the dark current is very good. And so we have demonstrated these high performance photo detectors. And then, of course, and everybody asks, how about the electrically pumped lasers? So in the past year or two, we have been focusing on, and how do we get enough quantum well and active material in the middle, and the cladding layer and the contact layer, and in order to have electrically pumped lasers. And this is kind of similar to the membranes lasers, and have the N-type and the P-type on the side, and then you can inject current to get them lasing. And this is, so we demonstrate that you can have a very uniform quantum well, and this vertical quantum wells that it's just grow laterally, and we find that there's no element mixing and so on. And with this material, again, we test them with some optically pumped lasers, and we make these micro-ring lasers, and we optically pump them, and again, we find them with this in-gas indium phosphide quantum well, and they can lace in the 1.5 micron band, and the threshold were quite low, so we are quite happy about this. And then we also, at the same time, we also try to incorporate the tapers, and in order to see how well we can couple the light in and out of these either lasers or photodetectors. And we find them with this silicon taper, because we've been growing this right on top of the oxide. So the silicon waveguide is kind of right next to it. So we can couple this light quite well with this taper. Again, with this, we can demonstrate a very high-speed photodetectors with a very low dark current. And you can see it from here. And also, this is the last slide I'm going to show you, that we use this lateral grown material to make DFB lasers, and there's micro-ring lasers that I showed you earlier. So the next I'm going to tell you about, I promise you, diversity. So this will be 3-nitride material from the micro LED micro display that we have been working on again for the past 20 years. And this is showing you this how 3.5 and 3-nitride actually combine with silicon, making this a micro display. So we, our focus is try to do this monolithically, and making this a micro LED array, and to make the full color micro displays. And we're starting with this 3-nitride material. It's either blue or green. So it's at the beginning, of course, it's monochromatic. And then later on, I'm going to tell you how do we get the full color. And actually, that's very, very challenging in how to get the full color, and combined with the silicon CMOS driver. And for this the technology for the display, this micro display, of course, you can use the traditional the LCD technology, and LCOS, the LCD on silicon, or you can make micro OLED. And then, of course, now many of the iWatch and some of the products are made with micro OLED. But we think that this micro LED is the ultimate solution for the AR, because you really need the brightness. and you need the brightness in order to see it under the daylight. And also using this 3 nitride, and the lifetime will be much better. Again, it's comparing with OLED. And also the speed and the power consumption will be lower. So that's what we have been focusing on, is working on this monolithic micro LED arrays. And so this also showing you the demand of depending on this display that you are trying to make for the large area display and the PPI, and also the medium size. And you can use LCOS, which is well developed, and you can use organic LEDs. And but then for the micro display, and you really need in the thousands, in the order of thousands pixels per inch. And this is for the AR and VR applications. And thus we think this micro LED is the ultimate solution, and or the quantum dot LED combined with the micro LED. So this is what we have. This is the two mainstream technology that people have been working on, the micro LED, micro display technology. One is they call the mass transfer because of this RGB problem. And so people have been doing the pick and place or the mass transfer. And then many of the big corporations have been focusing on using this technology. And we use a monolithic approach. And then some other companies are working on the same thing. And this is what we have been doing at the Hong Kong University of Science Technology. And I'll show you some of the advantage that doing it monolithically is that you don't have the small pixels to worry about, because in the old days we were working on the pixels of the tens of micron size, but now we're down to 2 microns. So with the millions and millions of pixels, and to do the pick and place, it's kind of hard. And then, but doing it monolithically using the all IC technology, and then this is, we think this would be the way to go. And then the disadvantage I was talking about, you only have a monochromatic depending on the starting wafers. So our solution is to do the color conversion. So you have the red quantum dot and the green quantum dot, and then you can have this full color display that I show you on the lower right-hand corner. And this is the quantum dot. It's, we did it 10 years ago, and we use the inkjet printing, and we find that, well, this is quite slow. It takes forever to make a display. So we didn't think that was a solution. And then, but later on, that we find this quantum dot photoresist. And now we can really use all IC microelectronics technology to make this full color monolithic process. And actually, we're starting with this gallium nitride LED material that's grown on silicon, and then have this IC driver. And right now, we're using 8-inch. And then we do the wafer bonding, and then we move the silicon substrate because it's not transparent. And then we work on this pixel technology to make individual pixels. And then we apply this quantum dot photoresist, and they're all spin coat, and you can see it from here. And we first apply this red quantum dot photoresist, and then this is using the 2 green and 1 red and 1 blue. And then this is how we make this full color display. And this, now we have this, the smallest micro LED micro display. And these, you can see the specification, and it has an excellent color gamut. And this, the weight is very small, and it has a very high contrast. It's over 2 million. And then also the speed is very high. And you can see it can cover quite a wide color combination. And this is contrast ratio is also very high. And this is, we call it the power match 1. And this is the 0.13. This is the full color display. And this is the smallest that we are making now. And we think it's sufficient for many applications. And the pixel pitch, the subpixel pitch, is 4 micron. And this will show you some of the display that you can see here. The full color display. And also we have this light engine, and that you can do the projection. And this is the slide that is showing you the projected images. The color is very good. And we have this AR glasses that here, if you want to take a look of this AR glasses, and you can see these images. And this one that I have is doesn't interact with the phone yet. And this is my team that have been working on this. I told you about for the past 15, 20 years. And thank you for your attention and to listen to this DII talk. Thank you. Thank you, thank you.
Thank you, Kei-Mei. This session is special because it allows us to recognize the professional work of our colleagues in presence of their peers. Each year, the IEEE Communication Society, the IEEE Photonics Society, and Optica recognize their fellows and other awards and honor recipients at OFC. These individuals are acknowledged for outstanding achievements in their respective fields across areas of research, applications, service, and leadership.
Whether these individuals are at the beginning of their careers or have already achieved a significant legacy of work, they personify the genius of innovation that inspires all of us here today. May I ask all fellows and award recipients in the audience today to stand, please? Everyone join us in congratulating all of the honorees. Our final award presentation is the John Tyndall Award, which recognizes outstanding contributions to fiber optic technology. It is one of the highest honors in our industry.
This year's honoree joins a highly distinguished list of past recipients. From Robert Marr and Donald Keck to Tingy Lee and Ivan Kamenow, these individuals have transformed how the world communicates and revolutionized how its inhabitants live and work.
The Tyndall Award is given to Masatoshi Suzuki of Chitose Institute of Science and Technology in Japan. He's recognized for his pioneering work in large-capacity, long-haul optical communication systems. Let's learn more about his work.
Speed, data density, and signal strength are critical to keeping us connected. Professor Masatoshi Suzuki's work over the last 40 years has developed some of the most important foundational technologies for enabling modern optical communications. After earning a PhD in electronics from Hokkaido University, Masatoshi joined the research laboratory of KDD, now KDDI. At the time, KDD was the only telecom company in Japan providing international telecommunication services via satellites and submarine cables. One of Masatoshi's first projects was to develop the high-speed and low-chirp light sources required for high-speed, long-haul optical transmission systems. He took a different research approach by focusing on external modulation, which resulted in the world's first high-speed, low-chirp EA modulators and EA modulator integrated DFB lasers. This breakthrough led to the current worldwide deployment of EMLs. He also demonstrated a very stable and flexible method to generate optical short pulses for high-speed optical soliton transmission. Devices developed from these technologies were introduced into many WDM submarine cable systems across the globe. In the mid-1990s, Masatoshi surprised the optical transmission community when his innovative research led to the new transmission scheme, Dispersion Managed Soliton, overcoming the Gordon-House limit in pure optical solitons. This provided a stable optical transmission of high-speed optical signals over long distances without timing jitter or waveform distortion. This discovery, which first enabled WDM long-haul optical transmission with high-speed signals, along with an international collaboration with ATT Submarine Systems and KDDI Group, resulted in a 200-fold increase in capacity for transoceanic submarine cable systems, supporting unparalleled growth for the global internet and society as a whole. Through his work with the KDDI Foundation, Masatoshi oversaw programs that provided resources to developing countries by building elementary schools, supporting art and music education, and installing fiber optic networks. An active member of the community, Masatoshi has co-authored 5 books and more than 420 peer-reviewed journal and conference papers, produced 120 registered international patents, and organized or participated in many international conferences. He's continuing his research at the Chitose Institute of Science and Technology and shares this advice, which has served him well throughout his career. Set specific, aspirational goals and stay committed until you achieve success. Then, share the fruits of your accomplishments.
Please welcome the recipient of the 2025 John Tyndall Award, Masatoshi Suzuki.
Good morning, ladies and gentlemen. It is my great honor to receive the prestigious John Tyndall Award, one of the highest honors in fiber optic societies. I'd like to express my sincere gratitude to the IEEE Photonic Society, Optica, for selecting me, as well as Corning. Since joining KDI laboratory, I have been engaged in research on high-capacity, long-distance optical communication systems. I have been fortunate to be the first to demonstrate 1 gigabit EML at OFC 1987, dispersion managed soliton in 1995 at OFC, 1 terabit transoceanic transmission and 10 petabit SDM transmission. This is equivalent to a capacity increase of 7 orders of magnitude within 30 years. All of this was done by team effort with my colleague at KDI laboratory, and many international collaborations have led to success. I'd like to take this opportunity to thank Professor Akira Hasegawa and Rin Morinawa of Bell Labs for intensive discussion of dispersion managed soliton, Neil Bangano and Peter Lange of AT&T SSI for the joint development of submarine cable system, Thomas Wood of Bell Labs for research collaboration on EA modulator, and Professor Yun Chang at KAIST for long-term collaborative research on optical access for 5G and beyond. Also, I'd like to thank my co-researcher, Shigeyuki Akiba, Noboru Edagawa, Itsuro Morita, Takehiro Tsuritani, Keiji Tanaka, Shu Yamamoto, Hideaki Tanaka, and Yuichi Matsushima, as well as all the members in Photonic Division of KDD Research for their continued team effort and enthusiasm to achieve the project success. Finally, as a recipient of John Tyndall Award, I'd like to promise to contribute to the sustainable growth of fiber optic society through human resource development of young researchers. Thank you for your kind attention.
It speaks to the strength of OFC that we have so many honorees in our midst. So much of their work have driven the discoveries that make this a truly transformative age. Congratulations to you all. Our final speaker is Dr. Bryan Robinson. As the head of the Optical and Quantum Communications Group at MIT Lincoln Lab, Bryan leads the development of laser communication systems for a variety of applications. Results from his work cross all planes, literally from undersea to land and space. Bryan was the lead systems engineer for the Lunar Laser Communications demonstration. This was NASA's first demonstration in 2013 of high-rate laser communications from space. On this project, he helped architect the laser communication system and oversaw development of the space and ground terminals. The laser terminal technology developed for that program continues to exert influence. It is the basis for NASA's laser communications relay demonstration. It has now evolved to a more capable design that will be developed on the upcoming Orion Artemis II mission, which will send humans to the moon next year. NASA has indicated that Artemis missions are a stepping stone to a manned mission to Mars. 1,000 times farther away than the moon, missions to Mars will require free space optics and optical communications to stay in contact with the crew and to send data back. Bryan's work will be an essential component when mankind takes its second giant leap in the near future. It is my great pleasure to introduce Bryan Robinson.
Thank you for that kind introduction. It's really a great privilege to be here today at this moment where Many years, in fact decades of development of these technologies have led to many recent successes. A few of those were just mentioned. I'm going to walk through some of those and tell you some things about where we might expect things to go in the future. But before I get to that, I guess keeping to the context of this historic conference, I thought it'd be useful to consider for a moment the remarkable development of human spaceflight that occurred in the 20th century. Looking back at the turn of the century in 1903, humans were just leaving the surface of the Earth for a few brief moments with those early demonstrations of flight by the Wright brothers. And less than 70 years later, humans were setting foot on the moon, and it's really quite remarkable. As a comm engineer, I'm equally impressed by the parallel development of wireless communications that took place over that same time period. In 1900, wireless communications were really just beginning. In 1901, Marconi did the first demonstration of transatlantic communications using radio waves. And this continued to develop over the ensuing decades to the point that when those humans eventually went to the moon in 1969, they carried with them a fairly sophisticated S-band radio that allowed them to remain in contact with the mission controllers back on Earth and allowed them to deliver what I'll highlight as one of several great moments in space communications, and allowed all of us back on Earth really to witness those first steps on the moon. A second great moment in space communications history that I'll highlight occurred about 20 years later. In 1980, the Voyager 1 mission had completed its primary mission after its encounter with Saturn. And at that time, the astronomer Carl Sagan thought it would be interesting to turn those cameras around on the spacecraft and point them back at Earth and take, if you will, a selfie with the longest ever invented selfie stick with the spacecraft about 6 billion kilometers away. In a great illustration of how challenging it can be to convince NASA space scientists and mission planners to change their plans and try something new, it actually took Sagan 10 years to convince them to undertake this feat. And the result of it you can see in this image on the left side of the chart, which shows space as viewed from Voyager at 6 billion kilometers away. And if you can see it, there's a very pale blue dot that is where we all exist. And this led to Sagan to share some pretty profound thoughts about what this image means for humanity and our place in the universe.
Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives.
So the value of the bits that these systems return is immensely valuable, not just for the scientific knowledge that they provide of the distant planets and other places that they visit, but also for the philosophical implications in our understanding of humanity's existence in this solar system. And so now I'd like to take just a few minutes and talk about what it takes to get those bits back from these vast distances to Earth, where we can appreciate their value. So the Voyager spacecraft, you can see here, was launched in 1977, just about 8 years after that Apollo 11 mission that put humans on the moon. It carried with it a state-of-the-art X-band transmitter that transmits 13 watts of data in the X-band. And then to direct that signal back to the Earth, it utilizes a large antenna. The larger you can make the antenna, the smaller the angular extent of the beam that it produces is. And in this case, they made the antenna as big as they could and still fit it within the fairing of the vehicle that launched the spacecraft. And so that turns out to be about 3.7 meters for Voyager. That 3.7 meter beam produces a 0.5 degree beam that's then directed back at the Earth. And to get a sense of how big that is, we can go back to this image of the pale blue dot, and I'll overlay the radio beam on top of that. And so you can see that that 13 watts of power is spread over an enormous area by the time it reaches Earth. The area of that circle is about 2 quadrillion square kilometers. A tiny, tiny fraction of it hits that fraction of a pixel that is Earth. And so then the game we play on the Earth is to build the biggest antenna we possibly can to point and receive that signal from space. And today, NASA has 3 sites around the globe that have 70-meter antennas that receive these signals from Voyager. And it's hard to get a sense of the scale of these antennas from a photograph like this. I tried to illustrate with a human silhouette down at the bottom, but really the area of this antenna is equivalent to the size of a football field, and it's mounted on a 2-axis gimbal that allows it to point anywhere in the sky and track these spacecraft as they move about their orbits. With that big antenna, the received power from Voyager is 3 × 10 to the minus 19 watts, or 300 zeptowatts, if you will. As an aside, if that were an optical signal, that's equivalent to about 2 photons per second at optical wavelengths. And through the magic of radio communications engineering that NASA has become a great expert at, they're able to translate that very, very weak signal into 160 bits per second of data returning from Voyager. And at that rate, it took about 2 months to deliver those photos of the pale blue dot back to Earth. So let's put that in perspective. This chart shows various data rates that we can operate with various places in space. And on the x-axis, I show space on a log scale. So on the left side, you can see things that are near Earth in low Earth orbit, and then going out to the farthest planets, Pluto and beyond on the right side, which are billions of kilometers away. And here's Voyager operating at 160 bits per second, out now beyond the limits of the solar system. Other systems that NASA has built in the years since include the Cassini mission, which went to Saturn and operated for about 20 years. At Saturn ranges, they can support data rates of about 14 kilobits per second. Coming even closer to Earth, we can look at systems at Mars. The Mars Reconnaissance Orbiter launched in 2005 and has been operating for more than 20 years now, delivering data rates at a peak of 2.6 megabits per second when Mars is close, and when Mars is further, a few hundred kilobits per second. And it's no coincidence that these missions all fall on a line. Every mission wants as much data as it can, but physics dictates how much we can return. And once we've maximized the power and size of the antennas involved, all that determines the data rate is the range, and the data rate decreases as the square of the range, and that's what gives you these data rates and the present capability of NASA's Deep Space Network. But where would we like to be in the future? I'm thinking about systems near Earth. We'd like to develop communication systems that can provide broadband services anywhere on the Earth. These would like to operate at 1s to hundreds of gigabits per second. Looking further out to the moon, as we seek to return to the moon and to have a sustained presence there, it's expected that data generated from the various missions going there will produce 1s to 10s of gigabits per second. And then looking further out to Mars for eventual human exploration of Mars, we need data rates of several hundred megabits per second. So these are well beyond the capabilities of radio frequency systems today by, in some cases, orders of magnitude. And the challenges here are pretty fundamental. To move vertically beyond what the current capabilities are requires spectrum. And in the radio domain, that's pretty much maxed out, and it's hard to get more than maybe a few tens of megahertz. If you're lucky, a gigahertz of bandwidth to communicate with, and that's a real limiter for data rate. Going out to the right on this plot requires more power, more directivity, and more sensitivity. And again, that's a challenge with current radio systems. But as it turns out, an invention that was produced in 1960 could provide a solution to both of these problems. In 1960, Ted Mayman demonstrated for the first time the laser. And actually, at the very first press conference announcing his success, he predicted, among various applications of this new invention, that lasers could be used to break through the existing barriers in spectrum that radio systems present, as well as an ability to use these for space communications and project light in very high intensity beams that can deliver more energy to a target and higher data rates. So that was 1960 when that goal was established. But it turns out the engineering of these systems was quite challenging. And 10 years later, IEEE Proceedings published a special issue on the current state of development for optical communication systems, and they pointed out that these systems remained very challenging to implement, and it wasn't even clear at that time when they would eventually become available. So I'm not going to go through the decades that followed and the many innovations that were eventually required to make this a success, but this being the Optical Fiber Communications Conference, I did want to highlight that much of the technology that makes today's system successful came out of the work that was developed and presented at this very conference through the years. On the left side, you can see here a representative lasercom terminal design from the 1980s that in this case used other technologies, in this case CD laser technologies that required free space alignment of all the various components, very difficult to integrate, test, and prepare for launch. In the middle, you can see what was developed in the 1990s, which started to incorporate the many components and technologies that were being developed for fiber telecommunications. These included high power, high reliability lasers and amplifiers, also efficient modulation techniques, as well as sensitive receivers that really became an enabler for these communication systems. And this leveraging of telecom technologies continues even today, where as telecom components have evolved to very highly integrated and capable high-rate transceivers, those very transceivers, it turns out, are suitable for space applications as well, and I'll show you some examples of that in a moment. So these developments led to the first lasercom success. In 2001, the US National Reconnaissance Office launched a satellite called Geolite. That carried a lasercom payload that was developed by Lincoln Laboratory and demonstrated for the first time space-based high-rate laser communications. A year later, they also made a link to a high-altitude aircraft and demonstrated that these techniques could be applied there as well. This led NASA to come and ask the question of, well, can we take that Geolite technology and send it to Mars? It turns out that the techniques used for Geolite don't scale well to Mars distances, and so we undertook some studies to develop a new architecture for deep space communications, leveraging, again, technologies that were coming about at that time in the early 2000s. And this eventually led to a demonstration at the Moon called the Lunar Laser Communication Demonstration in 2013, or LLCD. This was a lasercom payload that was installed on NASA's LADEE spacecraft. This is a small spacecraft that carried 3 fairly simple instruments, and those instruments relied on a primary radio downlink in the S-band, not too different from what the Apollo missions had carried, that operated at 100 kilobits per second. We put a lasercom terminal onto the spacecraft that you can see here. That lasercom terminal included a 10-centimeter optical telescope that was on a 2-axis gimbal and pointed the beam back at the Earth, transmitted an optical power of 0.5 watt. On the ground at Earth, we had a receiver that consisted of 4 40-centimeter telescopes for a total area of about 0.8 meters. And each of those telescopes was coupled to very high-efficiency superconducting nanowire single photon detectors. And that allowed us to demonstrate from the Moon, with this relatively small system, a data rate return of 622 megabits per second and a forward link of 20 megabits per second. We also proved in the process that you can point these narrow beams. I'll show you an illustration in a moment of what they look like. That can be done reliably, that you can send these signals through the Earth's atmosphere reliably. We showed that we could error-free downlink the entire spacecraft buffer in a mere minutes. And we showed that you could use multiple terminals to get around the effects of clouds and other atmospheric effects. Before leaving this demonstration, I'll just show you an illustration of what the size of a laser beam looks like. Here you can see in the center of the chart the ground station that we deployed in White Sands, New Mexico. As an aside, the radio telescopes that you can see on the right side of the chart, those are links to NASA's TDRS system, which actually operates at a similar data rate to what LLCD did at the Moon, but those operate 10 times closer to geosynchronous orbit. And those are 20-meter antennas compared to the 1-meter telescopes that LLCD used. So now I'll just start the animation. The red overlay represents what the laser spot would look like on the Earth. And when we get out far enough, you'll see that spot is about 6 kilometers in extent. Continuing to zoom out, you can see Las Cruces, New Mexico. You can see White Sands. Start to see the shape of the neighboring states. There's North America. Keep going. And there we are. So, and here's what it looks like at the Moon. The beam produced by that 10-centimeter aperture on LLCD is 15 micradians in extent, or about 1/1000th of a degree. And for perspective, as viewed from the Moon, the Earth is about 2 degrees in angular extent, and so that beam is 1/2000th of the diameter of the Earth. And obviously, a lot of the engineering that went into making these systems work involves how do you point these narrow beams, how do you keep them stably pointed on the target to deliver the energy to the receiver, and how do you establish and maintain those links. So I'm not going to go into the details of that. I'm going to stay focused on comm here. But that technology that was developed for LLCD, as was previously mentioned, then went on to impact a number of subsequent NASA demonstrations. NASA put up a relay in 2022 using similar sized terminals to relay data from ground and systems in space. In 2023, they installed a LaserComm terminal on the International Space Station that utilized that relay to send data down to the Earth at a gigabit per second, again, higher than what they can do with existing radio systems. And in a little less than a year, NASA will be returning humans to the moon for the first time aboard the Artemis II mission, which will go out to the moon and return, and it will carry a LaserComm link back to the Earth that will allow the astronauts to send high-rate data, enabling high-rate HD TV videos of the encounter, as well as downlink all of the data that the spacecraft generates during the mission. NASA has also sent these systems to deep space. NASA JPL developed a terminal called the Deep Space Optical Comm Terminal, or DSOC, that's installed on NASA's Psyche spacecraft that's headed to the Psyche asteroid. To date, that link has been demonstrated at ranges up to 3.3 AU, or 490 million kilometers. And it's shown that at those distances, they can support rates of many megabits per second, again, much higher than what you get for typical radio frequency returns. The apertures here are bigger. It's a 22 centimeter aperture on the spacecraft, and on the ground, they utilize a 5-meter telescope at Mount Palomar. But NASA and the US are not the only ones developing in this space. The German company TESAT was instrumental in some of the early demonstrations of this technology. In 2008, they demonstrated for the first time a LaserComm crosslink between 2 satellites in low Earth orbit. That technology was then further developed by TESAT in coordination with the European Space Agency and the German Space Agency, and today they have an operational relay in space with 2 terminals in geosynchronous space that are communicating with 4 terminals on low Earth orbiting platforms, and that can deliver now 40 terabytes of data per day, which again is an incredible amount of data for space systems. But the development didn't start there. Today, as I'm sure many of you are aware, there are a number of companies and agencies that are developing proliferated low Earth orbit systems to provide communications near Earth. Many of these systems are working to darken the skies with thousands of satellites in orbit that can provide high bandwidth links to anywhere on the globe in an untethered way. And these systems have system capacities that are vastly increased through the use of crosslinks between the satellites. And that's a relatively easy link to accomplish with LaserComm. It's space to space. You don't have to go through the Earth's atmosphere. And so most of these systems are actually developing that technology to support their systems. As an example, the SpaceX Starlink is really leading the way. Starlink reported at a conference a little more than a year ago that at that time they had launched 9,000 laser communication terminals as part of their constellation. These terminals operate at 200 gigabits per second. And at that time, they reported they were delivering more than 42 petabytes of daily traffic over those links. And that's, again, a phenomenal number from the perspective of space communications. And yet, these systems remain constrained by radio frequency links. They use radio frequency links to link to the users on the ground or in the air. And they also use radio frequency links to downlink the aggregated user data to the gateways that they have on the ground that then connect to the terrestrial networks. So LaserComm through the atmosphere is a challenge. And one last NASA demonstration I'll mention is the T-Bird demonstration, where we demonstrated that, in fact, you can do links through the Earth's atmosphere using standard telecom approaches. T-Bird was a mission on a CubeSat about the size of a shoebox that was launched to low Earth orbit in 2022. And we demonstrated with the mission that you can make robust data delivery at 200 gigabit per second rates through the Earth's atmosphere using standard off-the-shelf telecom communications technologies. We also demonstrated that with those links, which are only a few hundred kilometers in range, that you can simplify the optical design and actually steer the beam by body pointing the satellite rather than using sophisticated gimbal approaches. But you do have to deal with the fact that the atmosphere causes perturbations to the signal. And that comes about because refraction in the Earth's atmosphere distorts the optical signal as it propagates, and there's really 2 effects that it causes. One is called scintillation, which varies the amount of power that's collected in the aperture on the ground. And a second is the turbulence-induced phase errors that occur at the entrance aperture, which make it difficult to focus that beam down into a diffraction-limited spot to couple it to a single-mode fiber transceiver. Even using techniques such as adaptive optics, there is still residual power fluctuations that you have to deal with, and these telecom transceivers aren't designed to deal with such demonstrations. So for T-Bird, what we did is we developed a very simple wrapper around those telecom transceivers where we implemented an automatic repeat request scheme. We divided the transmitted data up into ARQ frames of about 15 megabytes. That's about a millisecond of data transmission at 100 gigabits per second. And when the power fluctuations caused the received power to drop below the COM threshold of these transceivers, we utilized an uplink, a very low data rate uplink of a couple kilobits per second to request retransmission of the frames that are lost. And this is a very efficient approach. It's capacity achieving on the erasure channel that's produced at the output of these transceivers, in the sense that each packet is only transmitted successfully once, and so we perfectly fill the channel that's provided, and we get, as a result, error-free contiguous data that was demonstrated as part of the mission. This is an example of what one of the passes for T-Bird looked like. So for systems operating from low Earth orbit direct to ground, the links are very short. It takes a few minutes from the time that the satellite first appears over the horizon to pass overhead and then set on the opposite horizon. And as it traverses that distance, the channel actually changes substantially. The range to the satellite varies, the shortest range being when it's directly overhead. And also the range through the atmosphere varies, with the most challenging atmosphere being near the horizon. Now, the effect of the ARQ system that we built is that the system automatically adjusts the throughput as the channel conditions change. And you can see an example of that in the middle plot here, where the system is operating at peak rates at 200 gigabits per second near the peak elevation, but at other times, lower rates were used to accommodate the atmospheric effects. And so this particular pass, we delivered 5 terabytes of data error-free in the 5-minute pass, which represents the highest data rate link from space to ground, as well as the largest data volume delivered from LEO to ground in a single pass. So with that success and the others that I've mentioned, we've already succeeded now with these free space laser communications in providing performance that extends beyond radio frequency capabilities by, in some cases, several orders of magnitude. And so these systems are already starting to transform the way we do communications today. I'd like to spend the last couple minutes here just talking about where further improvements can offer further enhancements in capability. I'll start by saying a few words about forward error correction. This curve shows the theoretical limit to receiver sensitivity that you can achieve with a dual polarization QPSK system like what telecom uses today. It was Claude Shannon back in the 1940s that taught us how to calculate these fundamental limits, and this shows the best that you can ever hope to do. Telecom systems today, they're interested in spectral efficiency, and so they operate with very low bandwidth expansion. They use 0.87 rate codes, and it turns out they're engineered pretty capably. With those high rate codes, they actually get to sensitivities of a few photons per bit, and only a couple of dB from this theoretical curve. And so that's quite impressive and certainly enabling for free space systems and minimizing the amount of power that's transmitted, although you can see that there's a lot of opportunity if we could reduce the rate. If we look at what T-Bird did, where we operated in the atmosphere, so these plots on the right show what the atmosphere looks like. This is a link with adaptive optics. The plot shows the time domain power received compared to the average power. And then the plot on the right shows the cumulative distribution of that power reception. It turns out that from a capacity perspective, that very noisy signal actually doesn't degrade the theoretical channel capacity very much. You can see the orange curve that I've overlaid shows what that degradation is. And in most cases, it's less than a fraction of a dB. But when we use the approach that T-Bird used, where we treat the output of that telecom transceiver as an erasure channel and use ARQ to get the bits through. In this particular case, if we receive the same average power as we had for the static channel, if you look at the cumulative distribution function, 50% of the time, the received power is below the threshold of the COM transceiver, and that means that our data throughput with these capacity-achieving ARQ codes is half of what we're actually transmitting. So we get 100 gigabits per second in this case through that turbulent atmosphere. And what you can see then is, on the bandwidth expansion scale as well, we're transmitting, modulating data at 200 gigabits per second and only getting 100 gigabits per second of throughput. And so where that star falls is actually about 8 dB from what the theoretical potential is if we could have better codes that are better designed for this type of atmosphere. And that 8 dB is pretty significant. For links from space to ground, that means you can have smaller apertures. you can have lower transmit powers, and you can support higher data rates. And so that can be very enabling for the types of low Earth orbiting systems that I've described. Another challenge that I've mentioned briefly is how do you couple signals received in these ground telescopes to optical fibers? The atmospheric turbulence increases the coupling losses. Traditionally, we use approaches like adaptive optics to correct for that. These systems can be complex and expensive. They can also require a fair amount of power because you have to have a wavefront sensor that can detect the phase distortions in the aperture and correct for them. And as a result, they incur losses. There's been a couple of approaches demonstrated recently that might offer improved performance. One of my colleagues at Lincoln Labs published a few years ago an approach where he used an array of very small apertures, and these apertures were small enough so that the atmospheric distortion across the aperture was small enough that you didn't need mechanical correction to that. Each aperture is then coupled to a coherent receiver, and the output is digitized. And then with digital signal processing, you can losslessly combine each of these coherent received signals to get a total collected power and of the aggregate that enables higher data rates. The folks at Nokia Bell Labs have demonstrated a similar approach where they could take a potentially larger aperture and couple it to a multi-mode fiber, and then demultiplex those multi-modes into single-mode fibers, and behind each of those fibers put a digital coherent receiver, and then again, with digital signal processing, losslessly combine those to get higher throughput. So these approaches really put the burden of the atmospheric correction into the digital domain, where we can leverage CMOS innovations to do that efficiently and to enable efficient coupling to the receiver. Lastly, I'll just note that coherent systems, in fact, are limited in the sensitivities that they can achieve, but that there are other approaches to receivers that can, in fact, do much better. Both the LLCD and the deep space optical comm missions that I mentioned use superconducting nanowire photon counting arrays. These arrays can detect and time individual photons that are collected by the telescope and use that to demonstrate very efficient communications. The green curve shows the theoretical sensitivity that's achievable with these types of systems. And you can see one example of performance shown there for the DSOC system at Mars max range type distances. They achieved 8 megabits per second, and they did that with less than a photon per bit, already beating the theoretical limits of coherent systems. And you can do even better by expanding the bandwidth further. In fact, a recent HERO demonstration from the folks at Nokia Bell Labs demonstrated 14 bits of information for each photon collected in their receiver. So pretty phenomenal. That relied on a factor of nearly 1 million in bandwidth expansion, so pretty challenging to implement in a practical system today. But nevertheless, something that we can envision for a future system. And to get there, we need, to do this at high data rates, we need high-rate, photon-efficient receivers. Today, these are typically limited to a few hundred megacounts per second, but there are ideas in the works for how to increase those count rates. You also need high bandwidth, high peak power transmitters. A factor of 1 million in bandwidth expansion means that you need 1 million times more modulation bandwidth than the data rate that you're communicating at, which can be very challenging to implement. And then finally, you need good spatial and spectral filtering at the receiver to reject the effects of background light, particularly in Earth-based receivers where sunlight can get into your receiver and substantially degrade the performance. But this is all in work, and these systems are conceivable in the very near future. And with those, we think we can achieve improvements in performance on the order of 10 dB or more of what current systems are demonstrating. So I'm going to end it there. I'll just state again that free space communications is a reality today. It's already enabling new types of systems here on Earth that can provide many gigabits per second of throughput to users anywhere on the surface. Future enhancements there can further enhance the system capacity of those networks. In the near future, humans will be returning to the moon. I mentioned that the first return will carry a lasercom communications terminal, but future infrastructure at the moon will support trunking of the many systems that are going to be there to provide high data rate links back to the Earth. And then in the not too distant future, I hope, humans will be setting foot on Mars. And the communication challenges to doing that at Mars can't really be overstated, but we already have in hand today an approach with optical communications that will enable high rate return from Mars as well as high rate forward links that will hopefully lead to the success of those future missions. So thank you for your attention.
Thank you, Bryan, for your inspiring talk.
This session has been an extraordinary glimpse at the diversity and the scale of our industry. Let's give thanks again to Pradeep, K-May, and Bryan.
So please join us tonight at 6:30 for the conference reception. It is held at the Marriott Marquis Hotel, just 2 blocks away at 4th and Mission.
And now the exhibition is open. We invite you to make your way downstairs where 685 companies are waiting to meet you. Thank you for being a part of OFC's 50th anniversary celebration. Have a
great week at OFC.